Okay. Okay, try now.
Right, yeah. So we're, yeah.
Right.
Yeah,
no
there we go.
question.
Okay, cool. Hey, Hey everyone, I'm Ryan. I'm CTO and co-founder at a company called DeepMirror. If you've not heard of us, we're trying to build software for medchems and compchems to help them prioritize which molecules to make next in their weekly or bi-weekly cycles. We have three main parts of the product. One is the predictive side, so build a model to predict molecular properties. We have a generation service, generate new molecules and score them. Then we also have co-folding. But today I'll be primarily talking about the predictive part of the system. Okay. So early stage drug discovery, we normally don't have much data. There's like a real data scarcity. And medchem teams or compchem teams need to be able to prioritize which compound to make. And we want to enable them to have the best chances of doing this. So you could take a structure-activity relationship approach, and you could have a chemist look over stuff and then reason about the chemistry to then prioritize. Or we could try and leverage some of the existing data that we have, build a model, and then predict. For example, if I have a bunch of molecules and I have PIC50, but I don't have a measurement, can we use the existing data to predict that empty gap? Okay. There's a lot of work around this, and we kind of always want to improve how good the predictions are of the models for two reasons. First one is that if you get better performance, like higher the chances when you do that prioritization, you're going to get something good. And then the other reason is sometimes this just doesn't work. You can't build a model. So is there anything that we can do for when you can't build a model to start getting something that's useful for the project? Okay. So this approach isn't new. The general way that you do this is that you have some program data. So this could be potency, it could be PK data, and you have some molecules and measurements. You convert that into a numerical representation, and this will be the main focus of the talk today. You have some learnable model. This could be a tree model, could be a machine learning model, but you can parameterize it on the data. You parameterize that, and then you get a learned model out, and then you can just use this model to make predictions. Okay. So then the question is, like, as a company, we have loads of users doing unique programs on the software. They upload data. It gets run through an AutoML pipeline that looks like this. How do we get the best configuration to make sure that they get the most? And we'll specifically talk about featureization choices today. Okay. Something that's been happening maybe the last year is talking about how we can integrate all the data that we have on Campbell or that's publicly available into these featureization methods. So the top 5 winners of the antiviral competition, both for potency and ADME, had taken all this vast amount of bioassay data and incorporated it into fingerprints. There's a really cool company in the States called Iambic, and they're taking this approach. And Recursion also had some work, and this is gaining a lot of traction publicly. But how well does this actually perform in practice? Okay. On the modeling side, I'm not going to go into this today, but when I talk about the predictions from the model, they'll be mainly Gaussian processes. We use them predominantly for 2 reasons. One, they work well on low data. So if you kind of have less than 100 or up to 10,000 data points, they're really good for modeling, and you get uncertainty. And you can use the uncertainty for downstream tasks like expected improvement, and you can use that for prioritization. If you want to know more about how we do that, I'm happy to speak afterwards. Trees and SVMs are also great in this low data regime. They don't have uncertainty. They're still good, but we need uncertainty in our modeling approaches. And then deep learning isn't great when you are on the 100 to kind of 10,000 approach. This is really good if you're a big pharma company and you have 500,000 solubility measurements. Like deep learning is the good choice there, but the other models don't scale so well. We have a paper from 2023 that kind of outlines more about this modeling, but we'll be sticking with Gaussian processes moving forwards. Okay. So then we have to convert the molecule into a numerical representation. And I see there being 2 main approaches for doing this. One is the cheminformatics approach. So we take what we know about physics, chemistry, information theory. We take a molecule and then we convert that into a vector. I'll go into a little bit more of some of the common ways to do this in RDKit. And then there's also machine learning approaches where we basically give a model to parameterize, expose it to some chemical language, and we say, hey, try and learn the cheminformatics rules, basically. Okay, so let's go into those in a little bit more detail. So the RDKit descriptors, I actually found the first commit from Greg in this file, and it was from 2006, which is crazy. So people have been using these descriptors to create these feature vectors. So you could say, okay, give me the molecular weight of the molecule, and then I'm going to put that in the first entry. You can compute a bunch of other properties like TSPA. You put that in, you keep enumerating over a ton of different properties to give you a feature vector. There's also Mordred, which we've found historically works really well, which is a feature vector of around 1800, more technical. Guillaume actually has a port of this into RDKit, which I'm super excited about because we've had speed issues with the Python implementation and it breaks production. But it's historically done well, so really excited for the C++ port. Hopefully we can finish that in hackathon. So these are kind of continuous variables in the feature vector, but then there's also binary vectors that we can make. For example, max keys. It's a curated list of smarts patterns, and they could say, does this molecule have a 5-membered ring? No, we put a 0 in that cell. Okay, so this is the kind of cheminformatics approach for featureization. And then we have the machine learning based approach. I think the first kind of ML approach that I'm aware of this is multivec. So you take fragments of smiles, you take a continuous bag of words model, which comes from language modeling, and then you learn on this in a semi-supervised fashion, and then you get an embedding. And then this is also done with transformers. More recently, you don't need any labels in this case. You just give it a language and you say, try and learn the rules of this language. Okay, so it's like a lazy approach to the cheminformatics feature vectors. More recently, and this is some cool work from the ChemProp team, Jackson, I think we'd had some discussions at the earlier RDKit meeting in Boston, and we were talking about Mordred descriptors are generally good, but they're slow to compute. So his idea was, can I take a GNN ChemProp, train against this dense matrix on the output, which is Mordred, and then get the GNN to basically learn the Mordred descriptors. And then there's like a shortcut way to get a feature vector. Okay, so I've talked a lot about the different ways to do this. And all the ways that I've spoken about are relying on physiochemical knowledge, structural chemistry, or information theory to construct these representations. But we have a very large body of data available that has assay measurements, okay? So is there any way that we can leverage this existing knowledge and get it into a fingerprint representation that we can use for the modeling? And the idea here is that if you can transfer some of the context of that data into the fingerprint, can we do better in the cases where the modeling approaches don't work, okay? So if you go and look at this data, it's very heterogeneous, it's difficult to work with. Greg has a paper saying, do not combine assay types from different sources. So for example, I shouldn't take my HLM measurements from lab A and B and then train a machine learning model end to end. And this is kind of like what all the data looks like. So we have this really sparse data representation. So our strategy to deal with this, instead of combining it together, why not just train end to end on a sparse matrix? So in this case, you take message passing graph neural network, you have an aggregation layer, then you have a feed forward part, and then you can just map to this sparse matrix. So the empty cells are cells where there's no data, the full cells are cells where there is data, and then we can do this for tons of assays using all the data from Campbell or other private sources. Okay. So just a bit more into like how we actually do the data preparation for this, because it's still kind of dirty when it comes from public sources or a range of different sources, is we extract the data, we canonicalize the molecules, we try and convert units into the same units where possible. There's loads of duplicates in this data, so you need to drop all of this. Outliers is a huge problem, so we do some filtering on that so we don't have extremes. And then we pivot the whole table into assay, unit, and source. Okay, so all the sources are separated out. And then we only keep data with a certain number of points. We don't want to have a column at the end of 1,000 by 100K matrix with one value. It's probably not going to be very useful. Okay, so we can do this procedure on multiple different sources, both public and private. Then we do an outer join on the smiles. So then unique smiles. We do a bit of QA on the output of this because sometimes distributions look very weird and you want things to look as normal as possible. And then we export this for machine learning. Okay, so then what we can do is we train this model end to end and then we cut off the head. So then you're just left with the aggregation layer. So the GNN has seen all of this data, and then we cut off the end that maps to that sparse array. And this is what we call the learned foundational fingerprints. And the hypothesis here is that now these fingerprints contain the context of all the public data sources that we have seen so far. Okay. So we're lucky enough that some of our users give us permission to share some of the metrics from running these auto ML pipelines. So then the question becomes, if we take all this private program data and then we have these different featureization methods, like what works well in practice, okay? So featureization method, model, in this case, Gaussian process, we run fivefold cross-validation. This data has not been in the fingerprinting, the pre-training step. And then we can take a look at how well things do, okay? So what we find is that it gives the highest R-squared value, which is a measure of the correlations between predicted and ground truth. And higher the number, the better. But what we also see is a bunch of classical methods, for example, Morgan, fingerprints, they are not significantly different. So what this means is what works best, well, it depends on your program. However, this can give an edge in predictive performance. And then the other thing that we can do is count the number of times which this featureizer is selected in the AutoML pipeline. So higher up this number is, that means more it was selected to be the best performing. And then we see in about 35% of data sets, this fingerprinting method is selected, followed by MapLight, which is a concatenation of classical. The interesting one here is actually Mordred and Chameleon, because Chameleon is actually trained on Mordred, but it does slightly better. It might be due to the embedding dimension. But what this means on a practical setting is that what works best really depends on the program, but we do see these featureizers come up more. Okay, some of you may not use Gaussian processes, so I just wanted to include a slide on the benchmarking of different models in this pipeline. So if you include support vector machines, random forest, and tree models, and what we do see here is that you really do see an improvement boost for Gaussian processes. This is probably because our pipeline is also highly optimized for Gaussian processes because we need the uncertainty, and you actually have to throw away some of the data for post-calibration for uncertainty quantification for these other methods. Okay, so kind of key take-homes is that you can use ADME and potency data and incorporate it into fingerprint representations to boost performance. But what works best on your individual program depends on the specific context. There isn't one that works best for them all. You need to try a range of them. And classical methods, like the ones that Greg had originally contributed in 2006, still do work great sometimes. I want to thank Daniel, who is mainly in charge of the machine learning service at Deep Mirror. I want to thank Guillaume and Jackson, who gave me some feedback on the presentation and have been answering loads of questions about Mordred. And then some of the companies who gave us permission today to share some of these metrics, including Richard from Amphista, who's here today. If you want to give this a go yourself, scan the QR code, you can test it against your featureizers. Thank you for listening, and I would be more than happy to take any questions.
Thank you very much. So we have questions there.
So it was because of the problem with the slides, for which I apologize.
Uh-huh.
I couldn't see the x-axis on your plots for this. Those were R squared.
Is R squared, yeah.
So none of those are particularly.
Uh-huh, yep.
But what I'm curious about is if you've looked at combining these things together, right? So taking your fingerprints from the activity and bioaffinities and combining that with, for example, the mortgage fingerprint, just concatenate.
Yeah, so we have that feature built into, oh, yeah. So the question from Greg was, how about concatenating these different features together? MapLight is actually an example of this. So that's like deep learning plus something else. We have the feature to do it in our current pipelines, but the number of combination kind of grows quite fast, and there's some kind of computational consequence for that. I think once the Mordred port is done, that's something that I'd be really keen to try, but we could try with Morgan fingerprints to get started. It's a great suggestion. Espen?
Okay, yeah, so my question is, now that you're using bioactivity technology, pre-trading data sets, what's often seen is that then when you come with a test set later on, it performs best if these molecules were already in the pre-training data set. And since a lot of it was public data, some of it is those data from deep mirror, what do you do to warn a user if you come with compounds that were already in the pre-training data?
Yeah, so in that case, there's no warning. So, the question is, in a production setting, if I then go and do a query on Campbell and then build a model, is the model performance going to be kind of not well represented because it was in the pre-training data? The answer to that is yes. There is no warning on it, but most of the use case for the software is on new program data. So that's where we would recommend that people use this.
Yeah, so I think there was one more.
Guillaume?
Also, the question, when you conjunct, you increase the relative, but when you ensemble all of them are better. So it's better to ensemble each of the model than to ensemble all of the model feature.
Okay, so Guillaume's point was to Greg's question before. A good strategy can just be build separate models and then take the ensemble average of those predictions. Yep.
Do you know what features are driving this? For example, when I use RDKit, normally log P is one of the large variances in it.
Yeah.
So are you really learning compounds that just do something and they're more likely to make a better outcome than compounds that don't?
We haven't looked into specifically what's been learnt in the pre-training, but I think that would be something interesting to explore. And I think there's a bunch of methods that you can use model agnostic to figure out which entries in that feature vector are contributing to the most of the prediction, but that's not something that we've looked at. But I think this has been mentioned before, that ideally you find which parts are correlated and then trim down the representation to get the most.